1687, Isaac Newton published Mathematical Principles of Natural Philosophy. It was one of the most impactful publications ever. It gave equations for gravity and the motion of objects. This idea of reducing natural phenomena to simple mathematical equations quickly caught on. Scientists all over the world began similarly working to break down their domains of study into simpler parts. They all hoped to reduce their fields into parts that were simple enough to describe with math, like Newton did with his, and this caused modern science to emerge from philosophy. But can everything be broken down this way? For 172 years, science focused almost exclusively on reductionism. That's when you try to understand things by reducing them into simpler parts. But while science was pushing in just this one consistent direction, nature was moving in two directions. Science helped the world understand many things, but there were also several topics that just couldn't seem to reduce. These included crystals, snowflakes, epidemiology, weather, social behavior, intelligence, and life itself. All of these seemed to defy simpler explanations. In 1859, at almost the midpoint between Newton's work and the present time, Charles Darwin published On the Origin of Species, another of the most impactful publications ever. It described how a simple natural process could cause complex life to emerge. This essentially removed one of the biggest blind spots in science. It opened the door for the studying of emergence. Emergence is the opposite of reductionism. Instead of trying to understand things by breaking them down, it seeks to understand how simple things can work together to build new and higher level properties, like intelligence, life, or memory. Science has had a little more than twice as long to explain reductionism to the general public, and most people seem to understand the concept very well. But emergence has faced some additional obstacles. For example, certain religious groups have even decided it conflicts with their cherished beliefs and have taken steps to prevent it from being taught effectively in schools. These days, emergence seems to be the most poorly understood half of science, so I'd like to talk about emergence. Emergence is when the whole entity has properties that are not found in its individual parts. As a simple example of emergence, consider a car. Cars have a property called locomotion. But which of the car's parts gives it this ability? It's not in the doors, it's not in the wheels, it's not even in the engine. It only exists when everything works together. In other words, locomotion is an emergent property. Next, consider a chair. Chairs provide a place for someone to sit. We might call this property chairness. But we don't have to make chairs out of smaller chairs. If you examine one part of a chair under a microscope, you might see wood fibers or plastic, but nothing that says, sit here. You may not even know you're looking at a part of a chair. Those parts don't have chairness. But together, those parts create a useful property that none of them provide alone. Some critics dismiss emergence, suggesting people just pull out this word when they don't really understand something. But emergence is not the same as magic. It is something that we can study and understand, and when we do, it opens many different fields of scientific exploration. So to prove this, let's talk about some very specific cases of emergence, and let's focus specifically on how emergence works. I'll start with a snowflake. Many snowflakes have 6 symmetric sides. How is that possible without some kind of intelligence guiding the formation of snowflakes? Clouds are made of small droplets of water. To keep this simple, let's model droplets of water as small spheres. When spheres freeze, they stick together. This will form equilateral triangles. And equilateral triangles naturally fit together to make hexagons. If they stick together tightly, they are more likely to last. And if they stick together poorly, well, they're more likely to just break apart again. So the 6-sided shape of snowflakes is nothing more than natural geometry. But what about all the amazing symmetry? How do you get 6 arms with similar structure from a bunch of chaotic spheres just blowing around in the wind? How does randomness create such symmetric and beautiful order? It's true that chaos is what puts the pieces together, but it is the natural conditions like humidity and temperature that determine which pieces will stay together. As the snowflake falls from a cloud and is blown around, it passes through many different conditions. But significantly, all 6 sides are exposed to the same conditions. So in the end, all the chaos becomes mostly irrelevant in the face of the persistent and steady force of natural filtering. Only the well-formed bonds last, so when the snowflake reaches the ground, each of its 6 sides encodes a record of all the atmospheric conditions through which that individual flake has passed. Another emergent phenomenon is intelligence. Individual neurons are not very intelligent, yet when they are all connected together in a brain, greater intelligence emerges. This is not mere speculation about how intelligence works. It is understood so thoroughly that we can, and do, build artificial intelligence out of parts that are not themselves intelligent. A common objection is that artificial intelligence is built by intelligent engineers, so maybe these engineers are just encoding their own intelligence into the machine. This is not a foolish concern. In fact, in the early days, that's actually how artificial intelligence was built. Engineers would encode rules that told the machine precisely how to behave under specific conditions. But there's a problem with that approach. It is limited by the intelligence of the engineer. And an engineer cannot possibly anticipate all the conditions under which the machine may need to operate. So these days, we use optimization algorithms. Optimization algorithms are simple processes that make gradual refinements, like sanding a rough piece of wood until it's smooth, one small change at a time. When you refine a cognitive model for many iterations, intelligence begins to emerge. Incidentally, natural evolution is also an iterative optimization process, so there are actually a great many parallels between the way artificial and natural intelligence had emerged. Now you can ask AI questions that its designer never even contemplated, and even questions that weren't represented in the training data. Yet it can still reason and respond with surprising effectiveness. As another example, let's examine how memory emerges in natural evolution. It is well understood that mutations have no memory. The same unhelpful mutations may occur in nature again and again. But evolution is not something that occurs in individuals. Evolution is something that occurs within populations. And at the level of populations, we see that something like memory does begin to emerge. The mutations that are unhelpful are purged more quickly from the population, while the relatively beneficial ones tend to be replicated more often. The result is that helpful mutations are effectively remembered within the population. Thus, even though mutations have no memories, evolution does have memory. Memory is an emergent phenomenon. Next, let's examine how foresight emerges in a brain. Imagine Valentine's Day is coming, and I must decide whether to celebrate by giving my wife chocolates or by dousing her with water. As each of these ideas occurs to me, I unconsciously simulate them in my mind to see how they are likely to play out. When I think of an idea, my brain instantly runs a little simulation. What will happen if I do this? Or what will happen if I do that? It's not a conscious process, it's just automatic. It's what brains do. As soon as I think of an idea, my brain immediately tests it in the simulated environment called my mind. And as I do this, I see that one of those two choices leads to consequences I prefer over the other. Specifically, one of them makes my wife happy, the other makes her unhappy. I do not like when my wife is unhappy, so naturally, when Valentine's Day comes around, I am more likely to gift my wife chocolates than I am to douse her with water. When I make choices with the outcome in mind, we say I have foresight. That's what foresight is. If foresight can emerge in the brain, can it also emerge in other systems, like artificial intelligence? What about natural evolution? It not only can, it does. Let's examine how this happens. Everyone knows evolution does not have a mind, so clearly it does not simulate its environment. Instead, nature uses the real environment to test candidate designs. But that's not foresight, it's testing without having the consequences in mind. That's pretty much the opposite of having foresight. But contemplate for a moment, what if you could see every dumb idea that flashes through my mind before I act? If you could see that, you might suppose I have no foresight either. It would just seem like I was testing every random idea that popped into my mind. Fortunately, for me, you cannot see all the ideas that I test in my mind. You only get to see the choices I judge to be worth repeating in the physical world. So the reason foresight emerges in my brain is because I can discard all those bad ideas before anyone even gets to see that I ever contemplated them. In nature, after a few generations, something very similar happens. All the bad designs will live and die, but the ones that are still being repeated after a few generations are usually the ones that played out well in the past. The mechanism in nature may be somewhat different than the mechanism in my brain, but the emergent outcome is very similar. Many candidate options are tested, and the ones that played out the best will get repeated. When effective designs begin to spread throughout the population, it looks like nature has been operating with foresight. Now, some might argue that's not real foresight, but what is real foresight? It is simply making the choices that lead to a desired consequence. And that is an emergent phenomenon that occurs in both brains and evolution. Now, to show that foresight really does emerge in evolution, let's consider a few very specific examples. People used to ask, what good is a heart if there's not already a circulatory system? And what good are veins and blood if there is no heart? Clearly, foresight is required to resolve this mutual dependency. But scientists eventually discovered primitive worms that actually had no hearts. These worms had to constantly wriggle in order to keep their blood circulating. But of course, that takes a lot of energy. We now understand that hearts evolved for a very specific purpose. That purpose is to accomplish the same task with a much lower cost in energy. However, this didn't answer all the questions. People still wondered, what good are veins if there is no blood? And what good is blood if there are no veins? This still seemed to be yet another dependency that would require foresight to resolve. Eventually, we discovered sea creatures with blood that was less like ours and more like filtered seawater. Gradually, we learned that blood itself evolved to make the transportation of nutrients more efficient. So once again, what initially looked like a chicken and egg problem actually turned out to be a stepwise process. Yet still, more objections followed. What good are veins if there are no organs? And how could organs survive without circulation? It seemed like all these complex and interdependent systems would need to emerge at the same time, and that would thwart the gradual nature of emergence. But just because people don't understand how something might emerge doesn't mean nature cannot find a way. Eventually, we discovered that primitive sponges have little distinction between their circulatory system and their digestive systems. Gradually, we began to understand that the whole circulatory system itself evolved to make the digestive system more efficient. Essentially, circulation is the second stage of digestion. There is a pattern that can be observed here. In hindsight, it often looks as if there are many dependencies within the systems of living creatures. Before we understand the evolutionary pathway by which these things evolved, it often looks like it would require intelligent foresight for these dependencies to form. And in a sense, that's not wrong. But intelligence and foresight are both phenomena that emerge from gradually refining ideas. And that is precisely what evolution does. Each small improvement makes the result look a little bit more intentional. So after many iterations, it starts to look like the product of a deliberate designer. Creationists like to use the term irreducibly complex, suggesting that some dependencies between two biological systems could not have formed gradually. But calling something irreducible assumes it can only be understood by breaking it down. Emergence is about understanding the processes that build something up. Reductionism just doesn't work for emergent phenomena. And ironically, complexity is actually beneficial to the process of emergence. If they understood this, they would seek for a dependency that was both irreducible and simple, not irreducibly complex. But no biological system of dependencies like that has ever been found. To illustrate why complexity actually benefits emergence, let's consider the problem of local optima. In artificial intelligence, we often compare gradual learning to a ball rolling down a hill. The ball cannot teleport, it has to find its way down step by step. Sometimes the ball might fall into a dip, not the lowest point, just a low point. This is what we call a local optimum. When the ball is in a local optimum, it cannot move by a small amount in any direction, because a small step in any direction would make the ball go up. That would seem to take it further away from its objective of going downhill. This is the condition creationists are suggesting occurs with irreducible complexity. They are suggesting that there is no gradual pathway to the state where we observe nature to be. They argue that nature must have skipped the steps, somehow teleported to a solution instead of rolling to that point gradually. But now let us consider the conditions necessary for a local optimum to occur. If the surface the ball is trying to roll down has only 2 dimensions, then a local optimum must block it from moving in the 4 cardinal directions, north, east, south, and west, or forward and backward in each of the 2 dimensions of the surface. This would be the case if your DNA encoded only 2 values, but your DNA actually encodes quite a lot more than just 2 values. In fact, human DNA contains about 3.2 billion nucleotides. That's a lot of directions in which the ball could potentially keep rolling. In order to be stuck in a local optimum, every single one of those directions would have to somehow make the creature less fit. If changing any one of those nucleotides actually made the creature better, then there is a gradual pathway for refinement, and it is not stuck in a local optimum. This is why complexity actually benefits emergence. The more complexity there is, the more possibilities there are for a gradual pathway of improvements. Perhaps mere human brains might miss the path, but nature is far more thorough. It explores using very large populations. Each creature in the population is essentially testing a different pathway, and evolution performs all these experiments simultaneously. That's more multitasking than any brain can handle. And it only takes one creature to find a useful mutation. That mutation can spread or fixate throughout the whole population. So emergence is almost inevitable in evolution. But that's not just a tendency of evolution, it's a tendency of all gradual optimization methods. It's how artificial intelligence works. It's how evolution works. It's how intelligence itself emerged. It's how planets arrived at orderly orbits. It's the reason snowflakes display beautiful symmetry, and it's the reason for crystals and social behavior. Emergence is not just a quirk of evolution, it's a common phenomenon of systems that improve gradually. Emergence is not magic, and it's not a buzzword. It is a surprising but real result of the laws of math and physics. It is a phenomenon that deserves serious attention from scientists, from engineers, from philosophers and thinkers, and from anyone who's ever wondered where intelligence came from. Our world appears to have formed gradually, but that does not mean it formed randomly. Rather, it is emergent.